As Jimmy mentioned, I'm Cameron Mott from SwRI, and I'll be presenting on our efforts to enable large-scale SPaT challenge deployments, specifically focusing on our project with GDOT in Atlanta, Georgia. So I'll be covering the following topics. I'm going to get into a little bit of background and give a bit of a shout out to Alan, who presented on a previous SPaT webinar on October 23rd on many of the same components that I'm going to discuss today. I'll go into a little bit more detail on some things and a little less detail on others. So I do highly recommend that SPaT webinar that's online and recorded for anybody to get some background if they're interested in additional items. Then I'm going to discuss some of the in-vehicle applications, and I'll provide some additional insight about our testing and validation efforts and our research into large-scale remote device management. I'm going to wrap it all up by bringing in some of the other projects where there are some synergies and some connections to this effort. And I do ask, I'm told that questions should be saved until the end of all of the presentations. But again, we welcome people to put in questions to the chat box on the right-hand side. All right, so let's get a little bit of context. We all are familiar with the SPaT Challenge website, highlighting some of the planned and some of the operational deployments across the nation. Many of us have a pin that's particularly of interest to us there. This one I'll be discussing will be the deployment in Atlanta, Georgia. This is under the direction of Alan Davis at GDOT, and Atkins and SwRI are working for GDOT. And I'll be covering a little bit more about what we're doing specifically for that. So we'll take a closer look at those activities in Atlanta to enable the deployment of SPaT and MAP at 54 signalized intersections, all in the heart of Atlanta, Georgia. It's a beautiful place. I highly recommend it. Just don't get lost on Peachtree Avenue. All right. So this one is the deployment across State Route 141. It's approximately 40 intersections and all along this particular corridor. Additionally, for those initial 54 intersections, there are also an additional 15 intersections all along State Route 8. Some of you may be familiar with State Route 8 from some of the demonstrations where we were demonstrating some of the SPaT and MAP deployment efforts as well. All right, so this deployment that I've been discussing so far is the deployment for the existing 54 signalized intersections. But coming up next, we'll be incorporating an additional 250 intersections and multiple RSU vendors. And I think that this is a real defining component to the vision for this particular project. It is large in scale, and those are some of the challenges that we get to tackle in terms of being able to solve this particular deployment for GDOT. So what does it take in each of those intersections? As depicted here, each of the intersections are including lane level maps with all the lanes as well as the connections. Many of you are probably very familiar with this. It's probably near and dear to your heart, or maybe a little of a bit of a frustration. But this is an interpretation of how the lanes are shown as received by our OBUs. So our application is receiving all of the map messages and getting all of the geometries out of that map message and then plotting it in a KML file in order to be visually represented, and we can utilize this for a number of verification purposes, as I will show in just a moment. I'm going to discuss a little bit about our in-vehicle applications. So these are our screens from our engineering user interface. This first application is the phase time remaining. And as I mentioned, the information for much of this has been covered already in a previous webinar. I'm going to talk through a bit of it, and you folks can keep an eye out for something that's of particular interest for you. So the phase time remaining gives the countdown for the number of seconds until the light changes to the next phase. It also indicates what that next phase will be by showing the countdown in the light for the next phase. So in this case, the next phase will be green in 4 seconds. And for this one, the next phase will be yellow in 17 seconds. This is just one example. We also have quite a bit of debug information that's available to us because, you know, we're engineers and we want to see a little bit more information. But it does allow us to depict the things that are important for travelers that are on the road right there at that intersection. And in this example, we can also display multiple movement phases for any of the relevant signals ahead of the vehicle. In this case, this is a left or straight lane, and we depict both because we don't have information about where the vehicle is intending to go. We just have information about where the vehicle is currently and an approximation of what we would expect the driver would need. The second application is the green speed application, and it helps drivers to make an informed decision regarding whether or not they will make it through the intersection during the current phase at their current speed. For this particular screen, if this were the scenario in front of this vehicle, I wouldn't really recommend that they speed through the intersection in order to make it. You can see here the depiction of the time remaining in seconds of 3 seconds and an indication of the target speed and the current speed. So this vehicle right now is traveling at 7 miles an hour, and in order to make it in the next 3 seconds, that 100 feet to the intersection, they'd need to speed up to 23 miles an hour. Now, given that's the next phase and they may want to go through it on a yellow, but it appears that this vehicle is slowing down already and it's unlikely given this information. But we are presenting it to drivers and of course allowing them to make their own much more informed decisions. The third application is a red light violation warning application that gives an indication to the driver if the vehicle is in danger of being in the intersection during a red, or in this case during an orange, yellow light rather, and allows them to have information about what's going on with the signal light. So in order to enable all of these, I'm going to move into a little bit more of our testing and validation efforts. This testing and validation, we are involved at all portions of the process, and having that kind of involvement can really make a large difference in being able to smooth things over. So for example, we can provide continuous improvement in terms of map interpretation and map encoding. And as one of those examples, we've been able to implement a number of verification algorithms that help to detect inconsistencies in the defined maps. Here are some of those errors for 3 of the intersections that have been detected by one of our algorithms. These intersections are all properly formatted, but the interpretation of the information is in some ways flawed. These 3 intersections show a connection to a lane which is not defined, and that is an indication that someone has put something into the map that maybe didn't complete all of the steps, or there was something that was just incorrect in terms of the lane numbers, for example. But this kind of an algorithm can detect those kinds of errors and then print out a flag or print out a log in order for us to go back and improve the map generation process. And then, of course, deploy them back out to the intersections and note that the errors are able to go away in that case. We also have the capability to do visual verification of the encoding of map data. Here's an example of a few of these, and if you're very familiar with them, you may be able to take a look at this and spot some of the issues that exist within these particular intersections. So on the top right intersection, as just one example, there are lanes that are defined as if they are egress, but they are supposed to be indicated as ingress lanes. In our tool in KML, we found that it's very handy to be able to color code the type of each of the lanes so that you can visually just take a glance at it and see that those lanes have been defined going out from the intersection, but in reality, those lanes should be coming in. On the picture on the left, one of the ingress lanes connects to an ingress lane from the opposite direction, instead of to an egress. That's a little bit more difficult to spot, but if you note the connects to, they're extraordinarily long in those cases. And we may even be able to, in the longer term, put in algorithmic checks for things like this. But for the moment, being able to look at the maps and seeing them as we do our verification, it kind of just, we see it and it pops out to us after being familiar with it. And by being able to view these interpretations of the maps, we can then improve their encoding and correct it for future deployment efforts. It turns out that many of these intersections are also very complex, both in their intersection geometry and their signal timing. And because we've been involved at all levels, we can provide some guidance on some ways to properly encode and interpret these more complex intersections. Some of these intersection issues are being addressed for the first time, at least that we're aware of. We hope to be able to provide guidance on what we've learned or even feedback to some of the standards committees regarding good practices. We've also run into that restriction on message size. I'm sure many of you are familiar with this. And we've come up with some possible options on how to be able to utilize some of the existing capabilities to reduce them, both in terms of reducing complexity, as well as being able to leverage some of the built-in mechanisms, such as remote intersection definitions. So in this case, this particular intersection is defined without egresses on the westbound lanes, and instead those westbound lanes are defined in another intersection as ingress, and the connects to can point to those remote intersections and show up as a connects to the ingress for the next intersection. In addition, one of the highlights from our project is our ability to forward messages from the field back to our lab. It allows us to monitor and verify some of those SPaT and map messages in real time from each of the signal controllers. This is a representation of the phase and time remaining for each of the phases based on the reports from the signal controllers. As you can note, there are still some improvements that are needed from the signal controllers. I really don't think that the minimum time remaining for these particular signals is 0, but we at least can see the current status of that particular lane, and it gives us an indication of what we would expect to see presented to drivers at that particular intersection. We also envision that BSMs can be forwarded from the field, providing additional insight and some data analysis capabilities. All right, so taking a look at the big picture, right now we're talking 54 intersections. We're going to be talking 250 intersections. We need a good way to do large-scale remote management of the RSUs that are enabling these kinds of SPaT deployments. And if we're going to be supporting 250, and even the following large-scale vision for GDOT includes 1,700 RSUs, even of multiple vendors, we're going to need some way to be able to manage them in bulk effectively. We need to be able to minimize the amount of time that an operator takes to interact with one of the RSUs or many of the RSUs. And we envision that this kind of improvement can occur through a screen like the one you see here, something that would be an RSU management screen with a program that can allow an operator to interact with those RSUs that are deployed in the field. They can see kind of at a glance the status of the various equipment, whether or not it's up and active, or in the cases where there's a red row, something that is not responding properly and may need some TLC or even a field visit. We also have the capability to do things like remote rebooting or even firmware updates that can be executed from this application. The example I'm showing here is a verification of the single device remote firmware update as we work on developing larger batch updates of multiple devices while being able to minimize that operator interaction that I was referring to. We think this is a mechanism that we can move forward with to allow for large-scale support for GDOT's remaining vision, and that this can be a valuable effort for others that are considering the possibility of doing large-scale deployments. All right, I'm going to talk a little bit about some of the project synergies So I'm always excited when I see areas where one project's efforts benefit another project and vice versa. Here are a few of them that we're aware of that we can bring up during the call. One of those is the next car effort, where we're focusing on being able to do powertrain optimization based on SPaT and also with MAP. So by utilizing that SPaT and MAP data, the vehicle's powertrain can be prepared for the upcoming intersection and in effect using less energy. We are utilizing a simulation environment called Transmodeler and some ground truth data that we've collected from a corridor in Dallas to be able to realize this challenge. We've got about a year and a half left. We're expecting a 20% improvement on top of the already incredible efficiency of the 54 mile per gallon hybrid that we're targeting for this effort. Another one of the projects that has some synergy with this effort is the Texas Connected Freight Corridor and some of the direct efforts that'll tie in well with this. The Texas Connected Freight Corridor, as Jianming will be able to fill in quite well on all of the efforts involved with that. We're focusing on a Texas triangle between many of the major Texas cities, especially those that have quite a bit of freight travel that goes between them. There are some direct efforts, including the SPaT corridor and truck signal prioritization that can benefit from the efforts regarding the SPaT and MAP deployments that we've been doing, as well as some of the enabling applications such as Q-warn, wrong way driving detection, and border wait times that can leverage some of the data that we would be getting from the field from things like BSMs or travel time predictions. So those are just a few of the projects that also have synergy with this existing project and being able to provide kind of a holistic improvement of all of the efforts involved. So in conclusion, we've gone through the background of GDOT's vision with 250 to even 1,700 intersections and multiple RSUs. I went over the three in-vehicle applications that are enabled through this effort, some of the testing and validation efforts that have been able to provide for this kind of capability, our vision for the large-scale remote device management and being able to handle with minimal operator interaction this large number of RSUs, and some additional project synergies. I appreciate the opportunity to present